My name is James Lee, and I serve as a team captain of the Rowan University Rocketry team. Rowan Rocketry is a student-led engineering clinic affiliated with the American Institute of Aeronautics and Astronautics that designs, builds, tests, and launches a 10,000-foot competition rocket for the International Rocket Engineering Competition, or IREC, held annually in Midland, Texas. IREC brings together over 150 universities from around the world to compete in precision high-power rocketry. Teams are judged not only on flight performance, but on the rigor of their engineering process, including structural analysis, propulsion integration, avionics development, recovery reliability, and payload design. Our team is made up of both mechanical and electrical and computer engineering students working across multiple subsystems: airframe, propulsion, avionics, recovery, payload, and management to build a fully integrated flight vehicle from the ground up. What makes Rowan Rocketry unique is that this isn't theoretical. Every calculation, every PCB, every layup, and every design decision culminates in a live launch in the Texas desert.
Hello, my name is Nolan Heaney, and I'm a senior mechanical engineering major at Rowan University and the sub-team lead for Rowan Rocketry's airframe and fins. The airframe is the structural backbone of the rocket. It houses critical subsystems like the payload, avionics bay, and recovery bay, while the fins provide aerodynamic stability as the vehicle accelerates to high speeds. During the fall semester, we mainly did a lot of simulation and buying components that were already commercial off the shelf, or COTS for short. This included the couplers, body tubing, and the 4-to-1 tangent ogive nose cone supplied to us by Wildman Rocketry. As far as the fins go, we had to do some on-site testing, so we had to get JMJ profile to machine G10 fiberglass samples for us to do. Currently, the airframe is in the final stages of assembly in this spring semester. We've completed carbon fiber surface preparation with forward shear pin integration, and we're now working on thermal management for the onboard camera and evaluating how the paint versus vinyl wrap that we are looking at could influence the performance of the rocket during IREC. With the structural system complete, I'll now hand it off to Kuba to discuss propulsion.
Hi, my name is Kuba Jagoda. I'm a mechanical engineering and physics student at Rowan University, and I lead the propulsion sub-team. The propulsion team's primary responsibilities were selecting and integrating the motor system that allows our rocket to reach its 10,000-foot target altitude. This includes performing calculations and simulations to properly size the motor for our rocket. Once a motor is selected, the motor needs to be integrated with the rest of the airframe. This includes manufacturing of the motor bulkheads, assembling the motor hardware, structurally bonding the fins and the bulkheads and the motor casing to the airframe. After the motor was fully integrated, our team shifted to the focus on the aerodynamic performance of our rocket. The boat tail is a component after the wings at the end of the airframe aimed at reducing aerodynamic drag on our rocket to increase its peak altitude. I'm currently working on computational fluid dynamic simulations in ANSYS Fluid aimed at verifying the drag on our rocket. These simulations are aimed at quantifying the reduction in drag for the boat tail's streamlined design. In parallel, Jakub Gaida played a key role in manufacturing the composite structures of the boat tail.
Hello, my name is Brody Schneider. I'm a junior mechanical engineering major, and I'm the recovery sub-team lead. The propulsion sub-team is responsible for getting the rocket off the ground. Our role on the recovery team is to ensure it returns safely. One of our primary responsibilities is selecting a parachute configuration that both complies with competition requirements and provides sufficient deceleration for a safe landing. To determine the optimal setup, we run dozens of simulations using OpenRocket, using real rocket construction data from the airframe and propulsion subsystems. These simulations allow us to accurately predict the rocket's flight profile and evaluate different recovery options. Based on that analysis, we selected this year's parachute configuration. We chose to reuse a proven system from a previous vehicle, a 3-foot drogue parachute for initial stabilization, and a 14-foot main parachute for final descent. After finalizing the parachute configuration, we then moved on to structural validation. Using SOLIDWORKS' finite element analysis tools, we simulated the loads experienced during parachute deployment. This ensures that components adjacent to the recovery system can withstand the expected forces. Where necessary, we refine and modify component designs to maintain appropriate factors of safety. The last major step that we have to complete in implementing the recovery system is ground testing. Because each parachute is housed in a separate bay, the rocket requires 2 explosive-driven separation events. These are achieved by using black powder charges, which are ignited by commands from the central flight computer. When triggered, the charges separate the rocket sections and deploy the parachutes. For ground testing, we're going to assemble the rocket as it will be configured on launch day, including the avionics bay, payload, and all recovery components. A simulated deployment command is sent from the flight computer to verify proper separation and parachute deployment. Successful ground tests confirm that the recovery system is ready for flight. Next up, I'll pass things over to our avionics subsystem.
Hello, my name is Marian Yanka, and I lead the avionics sub-team on Rowan Rocketry. Avionics is responsible for the flight computers that monitor and control the rocket throughout its mission. Using onboard sensors, our systems detect acceleration, orientation, and altitude in real time. Based on that data, the flight computers trigger deployment charges at precisely the right moment to ensure safe recovery. In addition to recovery deployment, our avionics systems transmit GPS location data so we can track and retrieve the rocket after landing, often miles downrange in the Texas desert. We also record barometric altitude data, which is critical because that measurement is what the IREC judges use to score our flight performance. To increase reliability, we use commercial off-the-shelf flight computers as our primary recovery and tracking systems. These provide proven competition-ready redundancy while we continue to expand our in-house development capabilities. Beyond the rocket itself, our ground station team is developing a more ruggedized field computer system capable of operating in the extreme desert conditions. As part of that effort, we are working on a semi-autonomous tracking antenna system that will improve real-time telemetry reception and lay the groundwork for future fully autonomous tracking integration. In parallel with our COTS systems, we are also developing a fully student-designed SRAD flight computer. I'll now hand it over to Marcello to explain more about that system and what it does.
Hello, my name is Marcello Basicchia, and I'm one of the avionics engineers working on our student researched and developed, or SRAD, flight computer. Our SRAD system is designed to perform everything a commercial off-the-shelf flight computer can do. This would be including sensing acceleration and orientation, detecting apogee, deploying recovery charges, logging flight data, and transmitting telemetry. The difference is that we design, build, and test every component ourselves. This year, we developed a modular testbed control board that allows us to validate each subsystem independently. This would be the microcontroller, the radio telemetry system, different sensors, pyro circuits, and much more. So by isolating each subsystem, we can rigorously test functionality and verify signal integrity and refine the power management before committing to a flight-ready design. So through this process, we gain hands-on experience in embedded systems, development, PCB design, hardware validation, and system-level integration. So using data from our test platform, we are now finalizing a fully flight-ready board that will be integrated directly into the rocket. So if our SRAD system performs successfully in competition, it not only improves our technical score, but also demonstrates our ability to engineer a complete, reliable avionics system from the ground up.
Hi, I'm Sarah, Logistics Coordinator for Rowan Rocketry, and I help oversee a lot of the managerial and back-end stuff. So some of my duties include planning expenses, tracking orders, and making sure everything gets placed in time for what the sub-teams may need. I help make sure that we stay within our funding limits, and in addition to that, I make sure that we're on track with deadlines, as well as funding and travel information, and I work closely with all of our sub-teams to communicate with them to see what they need. On top of that, I also help organize and lead our fundraising efforts to make sure that we have enough money within our budget, and I help manage our social media presence to keep everything informed of our team updates and progress, and I just try to step in wherever I'm needed to make sure that everything runs smoothly from an organizational standpoint.
Rowan Rocketry is a truly interdisciplinary effort that brings together engineers from all different backgrounds to design, build, and fly a real high-power rockets. Every subsystem you saw today represents months of design, testing, and collaboration from our team. We're incredibly grateful to our faculty, sponsors, and partners who support our work, and we're proud to represent Rowan University at the International Rocket Engineering Competition.